Hello everybody, today's topic is going to cover empirical formulas, and I will go over step by step a little review about what empirical formulas are and why they're important to learn. So empirical formulas by definition indicates the lowest whole number ratio of elements in a compound. So basically, if you think of fractions and how to reduce fractions, so for example like 2 over 2, that could be reduced down to 1 over 1. So in chemical equations and also compounds, specifically molecular compounds, you're going to have a different amount of each of these elements. And what you want to do is think about how they can get reduced down. The molecular formula is going to be the actual ratio of the elements in a compound. So again, let's think of, for example, water, right? H2O. That's actually a molecular formula. If you get something like H2O2, that is a molecular formula, but it can actually be reduced to an empirical formula. So the two can be the same. So in the example of water for H2O, it has already been reduced down, and it is also the molecular formula. CH2 is an empirical formula as another example. It's because you cannot reduce it any further. So it would be C1H2. The 1 is not written down on the carbon. While C2H4 is considered to be a molecular formula because you can technically reduce this down. So although the ratios are the same, the actual amount of elements is different. So if you reduce down the 4 right here, divide both numbers by 2 and 2, you get C1H2, dividing this one by 2. C3H6 is another example of a molecular formula. Can you tell me why it's a molecular formula? Well, it's because you can actually divide this number by 3 and 3, giving you C1H2, reducing it down to, again, an empirical formula. So all of these two are examples of a molecular formula. Well, this will be the empirical formula for that. H2O is an example, as I mentioned before. It is going to be considered both because you cannot reduce this down any further, but a molecular compound tells you the actual ratios. So let's talk about how to calculate empirical formulas real quick. All you have to do is find the lowest whole number ratio for empirical formula. So here's an example of C6H12O6. As you can see, it's a multiple of 6. So if you divide these numbers by 6, you can actually reduce those down. CH4N is another example of an empirical. So it's not just the ratio of the atoms, it's also the ratio of moles of atoms. So in other words, if we take a look at 1 mole of CO2, there is 1 mole of carbon and 2 moles of oxygen. So if you actually use this as a broken up into multiple parts, carbon dioxide can actually have 2 moles of O and 1 mole of C, or also 1 mole of CO2. So there's different ways of actually looking at this. In 1 molecule of CO2, there is 1 atom of C and also 2 atoms of O. So the way you would kind of say this is that it's the ratio of atoms and also the ratio of moles as well, of moles of those atoms. So let's talk about calculating that one. So the first step usually is going to be changing percent to grams, or converting the grams to moles for each element, and writing down the number of moles as a subscript in a chemical formula. Then what you would do next is you would divide each number by the lowest whole number, and then multiply the result by a whole number to get rid of any fractions if necessary. So you would not get any fractions on these type of problems. Alright, so here's an example. These are very common type of problems that you're going to get for calculating empirical formulas. So it says calculate the empirical formula of a compound of 38.67% to 16.22 of hydrogen and 45.11 of nitrogen. So as you can see, the percentages are actually useless to me. I need to convert those into moles in order to get them into the atoms. So our first step is to change it from a percentage to grams. And always assume 100 grams as the de facto number, as that's usually the easiest way to deal with it. So in our first example, we're going to multiply 38.67, and we're going to divide that to figure out how many moles we have. Now the 38.67 turns into 38.67 grams. because that's actually out of 100%. Now, in order to find the moles, you would divide this by the molar mass of carbon, which is 12.01, which gives you 3 moles of that. You would do the exact same thing for hydrogen. Because we only have one hydrogen in this case, we would use 1.01. Again, using the molar mass. Divide that, and that should give you 16.09 moles of hydrogen. And our last one, we would also do the exact same thing, but for nitrogen's mass, so you get 3. Now, the problem here is we have a bunch of decimal points. So our next step is to go ahead and write them down. But what we're going to do is divide it by the lowest one. That's going to give us our empirical formula. So in this case, 3.219 is our lowest number. So we're going to divide all numbers divided by 3.219. And that should give us our answer. So if we divide 3.219, we're going to get about a 1-to-1 mole of carbon and nitrogen. If we divide 16 divided by 3.219, we should get about a 5 mole of hydrogen. Now again, we're looking at whole numbers here. And because of that, looking at our whole number ratio, it's going to be C1H5N1, 1-to-1 ratio for the carbon to the nitrogen. So that gives us our 1 and a 1 here. And then the 5 moles of hydrogen to 1 mole ratio of that. And since you cannot divide this any further, and it is a whole number, that is our empirical formula. Now, let's see if you can try it out. Based off what I said, now you can pause the video right now and go ahead and see if you can do it. Okay, so hopefully you've already done it, and let's see what you get. So again, first step when you look at empirical formulas is go ahead and convert all of these into grams. And it's really easy because you just drop down the percentages. So it'll be 43.64. And if you do that, you should end up getting 43.6 grams divided by the molar mass of phosphorus, which is 30.97. That gives you 1.4. And then you also have 3.5 moles of O. Once you do that, you should get phosphorus of 1.4 and 3.5. You divide it by 1.4 for the phosphorus. And you should end up getting about a 2.5 to 1.4 moles. But the problem here is you want to multiply it to get rid of any of these fractions. So I usually would multiply it by a 2, and that gives you a P205. So if you're looking at a number that has a decimal point, you always want to get rid of that by multiplying by a number to get rid of it to get the next whole number. All right, let's do one more practice problem. In this specific case, we have caffeine, which is 49% carbon, 5% hydrogen, 28 nitrogen, and 16. What's the empirical formula off of that? So again, we're going to look at a 100-gram sample, take a look at how much on a percentage basis this one ends up being, and then backtracking the actual atoms themselves. And so if you actually do the numbers, again, doing the math here, it's basically saying that if I have a compound, I want to know exactly what the ratio of these atoms are based off the moles, because the moles are really also the ratio of these atoms. And so that's going to be the overarching concept that you'll find right there. So we divide the lowest number by the ratio, which is 1, and since they are close to whole numbers, we will use this as a formula. So in this specific case, you're going to find that these numbers are close enough that you don't actually have to multiply by another whole number. So you're going to keep those numbers, and you should end up with C4H5N2O1. So again, looking at percentages gives you a better idea of what that ratios for those numbers are. In order for you to determine whether something's empirical or molecular, you have to be able to divide it by the lowest whole number. In this specific case, you can see that the overall carbon percentage of the whole thing is a certain percentage based off of that. And so the empirical mass is 97 grams. Now, what if we want to go from empirical to molecular? Well, that's a pretty easy one. Since the empirical formula is the lowest ratio, the actual molecule would actually weigh more. So most of the time, I say always, molecular formulas are always going to weigh more than empiricals because you're obviously going to have to be adding molecules in there. Then you multiply by a whole number multiple to get that one. And then divide the actual molar mass by the mass of 1 mole of the empirical formula. So here's an example. Caffeine has a molar mass of 194. What is the molecular formula for that? So here's the example. So what we're going to do is we're going to take caffeine, which is 194, and we're going to divide that by the empirical formula mass for caffeine, and it's equal to a 2-to-1 ratio. Since we already know the empirical formula for caffeine, we're going to multiply it by 2. which is going to multiply all of that, which is going to give us our molecular formula of C8H10 and 4O2. So in order to figure out this ratio, you would always create the ratio of the molar mass by the empirical mass, which should give you the actual ratio itself. All right, here's a practice problem. Now, in these type of problems, you're going to get two things. You're going to get the percentages, so you have to go to empirical, and then from there, you can go to molecular. So we're going to have to take a two-step problem for this. All right, first step, we're going to go to the empirical first. So we're going to divide by 35.5 grams to give you the 2 moles. Then we're going to divide on the second one, the same idea, for the 12 grams for carbon, which gives us 2 moles. Again, we're using molar mass to do that. And then what we're going to do is divide by 1 gram for the hydrogen to give you the 4 moles. Now, in this specific case, we divide the lowest number by 2. Now, you probably cannot use this one. Now, a lot of people are probably going to say, well, what if I just use this one for the molecular formula? The problem is you don't know which one it is. So you have to use the mass given in the problem. So this would give you an empirical formula weight of 48.5 grams. So if you go ahead and add these up, you actually do have to calculate the mass, molar mass of the empirical formula. And its molar mass is known from gas density to be 98.96. So what's the molecular formula for this? So what you would end up doing is creating that ratio again of 98.96 divided by 48.5, which gives you 2. You're going to do the multiplication of that. So once you do that, you get the multiplication, and so your unidentified object or gas should be Cl2C2H4. Now, most of the time when they run these type of problems is they want you to identify the unknown formula for something based off the masses and the percentages. This could be a mass spec, or this could be any sort of instrumentation where you can actually calculate the percentages of certain elements, and they want you to backtrack to the molecular formula. So you will see this a lot in these type of problems where it's more of an investigative approach. All right, guys. Well, thank you very much, and that ends the lesson for empirical formulas.